The next topic of discussion that we're going to cover is spanning tree protocol. Spanning tree protocol was created by this lady named Radia Perlman back in the late 1970s, I believe, when she was working for Xerox. And it prevents loops or frames from looping around a network when redundant links are present between switches. Now, what does that mean? Now, if you look at this diagram over here on the left-hand side, you see that PC1 is connected to switch 1, and PC3 is connected to switch 3. Now, between switch 1 and switch 3, there are two paths. There are redundant links present, or there are redundant paths present. One is directly from switch 1 to switch 3, and the other one is from switch 1 to switch 2 to switch 4, and again, back to switch 3. So there are two paths between switch 1 and switch 3. One going this way, and one going this way. So let's pretend that PC1 sends a frame out to PC3. Now, switch 1 knows that PC3 exists going out port 1, and also PC3 exists going out port 2. Now let's pretend as that frame is being sent, this link between switch 3 and PC3 fails. So, the frame makes it to switch 1, and at this point, switch 1 does not know where PC3 is. Previously, switch 1 knew that PC3 is available either out port 1 or port 2. So what does a switch do with a frame where it doesn't know where the destination MAC is, or namely an unknown unicast frame? A unicast frame that's being sent where the destination is unknown. The switch floods it out. The switch floods it out port 1 and floods it out port 2. This frame that's moving in the clockwise direction, let's look at that first. It gets to switch 3. Switch 3 also does not know where PC3 is. So the switch floods it out port 2. This frame gets to switch 4. Switch 4 also doesn't know where PC3 is. Switch 4 floods it out its port to switch 2. The frame will get to switch 2, and switch 2 will again flood it out back to switch 1, and this process will continue. And this frame will continue looping in a clockwise direction in this network. The same thing will happen to the frame that was originally sent out switch 1, port 2, and it will start looping between switch 2, 4, 3, and 1 in a counterclockwise direction. So, this can eat up bandwidth unnecessarily, and eventually, if PC1 keeps transmitting frames to PC3, not knowing that PC3 is gone, this link is gone, enough frames will gather and start looping around the network that switch 1, 3, 4, and 2 will start crashing, or eventually will crash. This is called a layer 2 loop, or broadcast storm, actually. Sometimes called a broadcast storm. If PC1 sends out a broadcast, what happens to that? Again, a broadcast has flooded out all ports, and a frame will loop in a clockwise direction, and a frame will loop in a counterclockwise direction, and continue to loop till these switches crash. Now let's look at switch 3. What's happening at switch 3? Well, switch 3 gets this first frame from switch 1 that PC1 sends out, and switch 3 learns, reading the source MAC address field in the frame, that PC1 is available out port 1. Immediately after, the other frame that switch 1 sent out port 2 arrives at switch 3 port 2 after looping around the network, and switch 3 learns that, no, PC1 is available out port 2. So switch 1 modifies its MAC address table to reflect that PC1 is available out port 2. Immediately after, the frame looping in the counterclockwise direction arrives, and switch 3 again modifies its MAC address table and says, PC1 is available out of port 1. So what's happening is switch 3 is constantly updating its MAC address table and modifying it to say that PC1 is either available out of port 1, and then a second later, no, it's available out of port 2, then a second later, nope, it's available out of port 1. This is called trashing the MAC table. When you're trashing the MAC table, you're not actually making any forwarding decisions. Eventually, enough traffic will queue up on this switch that this switch will crash. So to prevent against this, spanning tree protocol shuts down redundant links between switches. So let's say if this topology was running spanning tree would maybe shut down this link. Now, when this link is shut down, there's only one path between PC1 and PC3, assuming that, this link is up and running. And there can't be any loops in this topology. So, when we move over to this topology, keep in mind, our end game with spanning tree is that some of these links are going to get shut down to prevent against layer 2 loops from happening. This was just drawn to show you the need for spanning tree and how loops can happen. It's not really part of your CCNA knowledge that you're supposed to know how these loops happen. You're just supposed to know that they can happen. You don't have to know how they happen. However, I felt the need to describe how a loop can happen. Now, spanning tree protocol, as I said, works to prevent loops between switched devices or switches when there are redundant links present. Do we have redundant links here in this topology? We have switch 1, 2, 3, and 4 connected together. So a loop can form going this way or the other way. And then we have switch 2 and 4 connected together on port 2 and port 3 on both switches, and you may get a loop going this way. Now, upon power up, when all these switches are powered up, they start sending spanning tree protocol frames to each other by default. Spanning tree is on all switches by default. And it is highly recommended that you don't turn it off. You may turn it off under certain circumstances, and I will tell you how at the end of this lecture, but it is recommended that you don't turn spanning tree off. Now, when these switches power up, and just to quickly elaborate on this topology, switch 1 is connected to switch 3 on port 2 on both sides, on switch 1 and switch 3. Switch 2 is connected to switch 4 on port 2 and port 3. And switch 1 is connected to switch 2 on port 1. And switch 3 is connected to switch 4, both sides on port 1. The AAAA, CCCC, BBBB, and DDDD are the MAC addresses of these respective switches. Now, once again, I know this is only 16 bits. Each hex character is 4 bits, making 16 bits instead of 48, but it just makes the diagram cleaner on board instead of me having to write 48 bits worth of A's. Now, when these switches power up, by default, they start sending each other spanning tree protocol frames called BPDUs. BPDU stands for a Bridge Protocol Data Unit. These BPDUs are sent every 2 seconds out all ports. So, for example, switch 1 will be sending out BPDUs out port Fast Ethernet 02 and port Fast Ethernet 01 every 2 seconds. Keeping in mind that switches send BPDUs every 2 seconds to each other upon power up. Now, spanning tree works in 3 steps. So for spanning tree to go from nothing, from just starting up, to it converging, and by converging I mean some of these links will get shut down, it does that in 3 steps. So step 1 for spanning tree is elect one root bridge per layer 2 domain. Step 2 is elect one root port per non-root switch. And I know these don't make sense yet. They're not supposed to. I'm just going over the 3 steps that you need to make spanning tree converge, and then we're going to explore each step in detail. So the 3rd step is elect one designated port per segment. So step 1 is elect one root bridge per layer 2 domain. So this is our layer 2 domain. Out of these 4 switches, we're going to elect one switch to be something called the root bridge. Then elect one root port per non-root switch. So for the switches that are not the root bridge, we're going to elect something called a root port. And then we're going to elect one designated port per segment. And a segment is the link between two switches. So this is a segment between switch 1 and switch 3. This is a segment between switch 1 and switch 2. This is a segment between switch 3 and switch 4. And these are two segments between switch 2 and switch 4. So there are a total of 1, 2, 3, 4, 5 segments in this network. Now, each one of these spanning tree steps needs to follow this 4-step spanning tree decision process. So for each one of these steps, we're going to follow the spanning tree decision process, which is a 4-step process. And we're going to stop at the process which works. So for root bridge election, we're going to go top down, and we're going to stop at the process that elects the root bridge. For root port election, we're going to go top down, and we're going to stop at the process that elects the root port. And same with the designated port, we're going to go top down and stop at the process that elects the designated port. So the first step is electing a root bridge. Now, I said that each one of these switches, when they power up, start sending bridge protocol data units to each other every 2 seconds. I hope you have taken note that there are 3 steps for spanning tree to converge. Step 1 is electing a root bridge per layer 2 domain. Once again, step 2 is electing a root port per non-root switch. For all switches that are not the root bridge, we're going to elect something called the root port. And step 3 is elect one designated port per segment.